Good morning, everybody.
Good morning.
And welcome back. Okay, so the previous class we started talking about the compensators. So what we're going to be doing today is we're going to be continuing the discussion of the compensators. We're going to be looking at the lag compensator. And then we're going to look at the PD controller. And then next we're going to look at the lead compensator. And finally we're going to look at the PID controller. Okay, so just to refresh your memory on what we've been trying to do, we said we're going to try to use the root locus, our knowledge of the root locus, to design a controller to improve the performance of a system. And we said if you want to improve the performance of the system, we can either improve the steady state error or we're going to improve the transient response. And then we said if we trying to improve the steady state error, we're going to look at two types of controllers. The first one that we studied was the PI controller. And the idea was to increase the system type by 1. And therefore, we know the higher the system type, the lower the steady state error. So that was the idea behind the PI controller. Then we said we're going to look at the lag compensator, which we're going to be looking at now. Now, we also said the difference between the PID controller and the lag compensator. This one uses an active circuit, requires an op-amp, while the lag compensator is just a passive circuit, does not require an active circuit. And then we're going to look at the improvement of the transient response, and we're going to be looking at the PD controller, which is the proportional plus derivative, and then we're going to be looking at the lead compensator. And similar to the improvement of the steady state, the PD compensator uses an active circuit, while the lead compensator uses a passive circuit. Okay, so with that, we can look at the next compensator. So in the previous class, we looked at the PI controller. Now we're going to look at the lag compensator. Okay, so again, this uses a passive circuit. And the circuit for the lag compensator looks something like this. We have R1, we have R2, and we have a capacitor. We have V input, we have V output. And if I calculate the transfer function, V output over V input, we can write this as R2 over 1 plus R2 multiplied by S plus 1 over R2 R2 multiplied by C divided by S plus 1 over R1 plus R2 multiplied by C. So this is the transfer function of the lag compensator. Now if I plot the poles and zeros that the lag compensator are going to add to the system, I'm going to have a pole closer to the j omega axis and a zero that is farther away. So we can write this as K multiplied by S plus ZC divided by S plus PC, where PC is smaller than ZC. Together? In the case of the PI controller, we chose this pole to be at the origin, and then we have a zero. In the case of the lag compensator, we can no longer put this at the origin. Therefore, we try to put it as close to the j omega axis as possible. Okay, So let's see how does the lag compensator work. Again, we use the lag compensator to improve the steady state error. And to understand how it improves the steady state error, let's say that we have a plant, G of S, that is given by K multiplied by S plus Z1 multiplied by S plus Z2, etc., divided by S multiplied by S plus P1 multiplied by S plus P2, etc. So we have a system, G of S, that we're going to improve the steady state error for. So we came to this system and we calculated the velocity constant. Kv is equal to the limit as S goes to 0 of S multiplied by G of S. If you remember from the steady state error calculations, the velocity constant is equal to the limit of S multiplied by G of S. And therefore, this is going to equal to K multiplied by Z1 multiplied by Z2, etc., divided by P1 multiplied by P2, etc. And this is our velocity constant. Okay. So this is the uncompensated system. This is how we calculated the steady state error. We calculate the velocity constant. Now we're going to look at what happens when we add a controller to this system. So if we have GC of S added to the system, the calculation of KV is going to change. We're going to have KV new, which is going to equal to the same formula, the limit as S goes to 0 of G of S multiplied by G controller. So this is going to be the limit as S goes to 0 of S multiplied by G of S multiplied by the G controller of S. And this is going to equal to K multiplied by Z1 multiplied by Z2 divided by P1 multiplied by P2. But now we're going to be adding the controller to it, and therefore we're going to, so this is etc., etc., multiplied by ZC divided by PC. Is that clear? Does that make sense? So originally we have only G of S in the system. Now we have G of S and we have the G controller, GC and G of S. And therefore, when we calculate the KV, we're going to take into account both the poles and zeros of both of these systems. This was the original one that came from G of S, but then we have ZC over PC that comes from the controller from here. Is that clear, everybody? Okay. So therefore, if we look at what happened to KV, if I calculate KV new divided by the original KV, what is this going to equal to? The improvement in KV. If I take KV over KV new divided by KV, what is it going to equal to? This term is common, and therefore going to cancel out. The only thing that is going to be left is ZC divided by PC. So this is equal the improvement in the steady state error. And of course, ZC over PC is greater than 1 by choice because we choose ZC to be greater than PC. Okay. Let's do an example and calculate the an example on the calculation of the improvement using a lag compensator. So we have the system is operating with Kp that is equal to 8.23 and zeta is equal to 0.174. And we want to improve we're going to design a lag compensator to improve steady state error by a factor of 10. Okay. So this example we've done before. And if you recall, when we calculate Kp, we got the steady state error that is 1 over 1 plus Kp, and it was equal to 0.108 from the previous lecture. So I'm going to write here from lecture 20. We calculated the steady state error and it was equal to 0.108, which is equal to 1 over 1 plus Kp, and Kp was equal to 164 divided by 1 times 2 times 10. Okay, so we want to improve the steady state error by 10 folds. So therefore, E steady state nu is going to equal to 0.108 divided by 10, which is going to equal to 0.10108. Which is going to equal to 0.0108. So this is the current steady state error. We're going to improve it by a factor of 10. So we want the new steady state error to be equal to 0.0108. Now this new steady state error is going to equal to 1 over 1 plus Kp nu. Together? And therefore, Kp nu is going to equal to 91.59. Now this Kp nu, the improvement in Kp nu is the ratio of Zc divided by Pc. So therefore, Kp nu divided by Kp, the original Kp, is going to equal to 91.59 divided by Kp, which was equal to, which used to equal to 8.23. which is going to equal 11.13. Now this improvement is going to come from ZC divided by PC. And therefore, we want our compensator to have a ratio of ZC over PC that is equal to 11.13. We can arbitrarily select the locations. We can select PC to equal to 0.01. And this will give me ZC that is equal to 11.13 multiplied by PC, which is going to equal to 0.111. Is that clear? Everybody? Anybody understood the example? Okay. So therefore, we're going to have our PC at negative 0.01, and we're going to have our ZC at negative 0.11, and we're going to have our operating point almost at the same location it used to be. Is that clear? So again, we're adding a pole and a zero very close to each other, so they'll have minimum impact on the root locus, and therefore I'm going to stay operating very close to where I used to operate on the root locus. However, the ratio of ZC over PC is going to improve the constants that we use in the calculation of the error, and therefore I'm going to have an improvement in the steady state error by the ratio of ZC divided by PC. Any questions? Questions? No? Okay. Okay, before we move on to the next compensators that we're going to look at, let's just look at what this lag compensators do. So if I look at the example that we just done, now let's open MATLAB and just plot the frequency response for it. Okay, so this is the frequency response of the compensator, of a compensator. So this was the using frag x 1, 1, comma 1.1. So I have a 0 at negative 1, and I have a pole at negative 0.1. Together? What does this look like? A low pass filter. Excellent. A low pass filter. So what is it I'm doing in this system with this compensator? I'm taking the error signal and I'm passing it through a low pass filter. And in doing so, what happens to the steady state error? It gets reduced. We reduce the steady state error. Now what happens when we have a low pass filter? So if I have a low-pass filter here, and I applied a square root to this low-pass filter, how does the output gonna look like at the output of the low-pass filter? It's gonna look something like this. Agree? Like think of an RC circuit, a first order RC circuit. It's going to charge, discharge, low pass filter. The high frequency component that enables me to jump from 0 to a value are removed. Therefore, I cannot jump from this value to this value. You see that? In order for me to be able to go from 0 to this value, I need to be able to have a high frequency components. If I remove these high frequency components, then the signal can only go to that value gradually. Make sense? Okay. Now what happens if I have an integrator? What happens if I apply a high frequency signal like this? What is the output of this integrator? Okay, let's see what happens if I apply this signal, and then if I apply this signal, which is a constant, then apply this signal, which is very low frequency. So this is high frequency. This is DC, which is constant, and this is low frequency. So what happens if I apply these three signals to this integrator? I'm going to be integrating this. So at this point, the integration is 0. Then I'm going to start integrating the area. I have this area. So I'm going to have a maximum value. Then I'm going to start adding negative area. At this point, I'm going to have a 0. The same thing. I'm going to have area going up to a maximum, then going back to a 0. Maximum going back to a 0. So I'm going to have something like this. Oops, it's going to be always positive. Make sense? Now if I have a very low frequency, what's going to happen? What is the output of this integrator going to be? It's going to be a ramp. I'm going to integrate it from here. Where the signal is going to start going up. If I have a lower frequency, what is the output going to be? The signal is going to be getting higher and higher and higher. Then I'm going to start adding the negative, and it's going to go back to a 0. So what does the integrator act like? High pass filter, low pass filter, band pass filter. What else? More accurately than band pass. It acts like a low pass filter. Low frequencies, I mean, if this is the lowest frequency, it went through and get larger and larger. I increase the frequency, it still got bigger. I increase the frequency, all of a sudden, it got smaller. If I increase the frequency even more, if I come here, I increase the frequency, even higher frequency. What is the output going to be? Even smaller and smaller. Together? So therefore, the integrator is going to act like a low-pass filter. Okay. So again, what I'm trying to say, is that when we improve the steady state error, we added 1 over S, increases the system type, we improve the steady state error. We said this acts like a low pass filter, so this is consistent. The lag compensator is also a low pass filter. So any low pass filter is going to improve the steady state error. Make sense? Okay. Now just to cover the other case, what happens if I have a derivative? What does a derivative act like? If I applied a constant signal to it, what is the output going to equal to? 0. And if I apply a sinusoidal signal, what is the output going to be? What is it? A sinusoid is going to be bigger or smaller? Bigger. It's going to be omega 0 multiplied by sine omega 0. So therefore, what happened to this sinusoid is going to be scaled by the frequency. So if this is omega, it's going to be multiplied by 1,000,000. So therefore, this is going to get much, much bigger. So therefore, what does a derivative act like? A high-pass filter. Okay. So you see, if that signal is constant, there is no changes, the high-pass filter remove that signal. If there are changes between a value and the previous value, the high-pass filter or the derivative will amplify that difference. Make sense? Okay, so keep that in mind as we look at the different compensators, because you can see it, or it will help you better understand how these compensators are working. Again, this is a low-pass filter, which is the lag compensator. Increasing the system type by 1 using an integrator is a low-pass filter, and it is consistent. Adding a low-pass filter will improve the steady-state error. Okay. And remember how the increasing the system type by 1 improved the steady-state error? Does anybody remember? How? Increasing the system type by 1 improved the steady-state error. Anybody remember?
How does it?
What is it?
How does it do that? Oh, you're like adding more holes on.
And
In that.
I have an error signal that looks like this. So if I'm looking at my system, I have an error signal between the input and the output. Let's say it looks like this, very tiny signal here. If I took it through a low-pass filter or through an integrator, what's going to happen to it? It's going to get bigger. The low-pass filter is going to get bigger. And therefore, if this is a motor that I'm trying to move to a certain position, that error signal is getting bigger and bigger, and therefore is going to drive the motor to move to reduce that error. Does that make sense? And the same thing happens with all these low-pass filters. Very small signal gets amplified by the integrator. This by itself is not able to, this error signal is not enough, for instance, to drive the motor. But if I have this error, with time, this signal is going to get bigger, bigger, enough to drive the motor to the right place to reduce that error. It's going to keep doing it till that error is so tiny that even after I amplify it, it's not enough to drive the motor. And therefore, that means that error is so small, either 0 or very small. Together?
So you're trying to amplify the error so that you
Yes, I'm trying to make the
Okay.
error bigger, so it will drive the motor.
So the motor runs just by trying to correct a mistake?
By trying to, yes, by trying, not a mistake, by trying to reduce the error.
Well,
Can we do this in lab?
this is
Do we do
blowing
this in
my
lab?
mind right now.
We're going to do this in lab. We're going to do a lab with a motor that we control our speed with.
Which is like overshooting each other.
But this is, I mean, we look at the math, we understand the math, it makes sense. But this is what the physics behind the math. That's how this is working. Okay. Okay. Moving on to our next set of compensators. We're going to look at the improvement or improving the transient response. And therefore, we're going to be looking at two types of compensators. As we said at the beginning, we're going to be looking at the PD compensator, which has a transfer function that is z plus zs. It does not have a pole, just has a 0. And this uses an active circuit. And we're going to have a lead compensator, which has a transfer function of S plus ZC divided by S plus PC. And when you look at the lead compensator, it has the same form as the lag compensator. What's the difference between them? The locations that we choose for the poles and zeros. Which one is bigger? Okay, so let's start with the proportional plus derivative compensator. So this uses an active circuit. So the circuit for the PD compensator or controller looks something like this. This is R2, this is C, this is R1, this is the input, this is the output, and we can write V output over V input is going to equal to negative R2 over the impedance of the equivalent parallel, which we can write as 1 plus S C R1 divided by R1. And therefore, we can write this as negative R2 multiplied by C multiplied by S plus 1 over R1 multiplied by C. Together? And we can also write this as a gain K multiplied by S plus ZC. So all these are equivalent from the circuit that we have here of the op-amp. Okay, so what are we doing with the proportional plus derivative? We're going to take our error signal. So this is our error signal. And what are we doing to this error signal? We're going to take it through a constant K, and then we're going to multiply it by S. We're going to take it through a K, and we're going to multiply it by ZC. And then we're going to add these together. And this is going to be K multiplied by S plus K multiplied by ZC multiplied by the error signal. And then we're going to take it and apply it to our plant. And we're going to take the output and we're going to feed it back. Together? Make sense? This is our compensator, which is K multiplied by S plus ZC. What is this? K multiplied by S plus K multiplied by ZC. So any signal, we're multiplying it by K multiplied by S, K multiplied by ZC. Everybody can see this? Okay. Again, this is output over input. So what's happening to the error signal? It's going to get multiplied by a constant here. And then what is it going to get multiplied by? A derivative. What is it the derivative going to do? Yes, it's going to amplify the changes in the error signal. Together? It's going to amplify, similar to what we've seen here. It's going to amplify the changes in the signal. If the signal is constant, the derivative is not going to do anything. It's going to just remove the signal. If the signal is changing, it's going to amplify these changes. Okay. So let's see how we're going to design a PD controller of a system. So I'm going to design a derivative compensator to yield 16% overshoot with reduction in settling time by 3 folds. Okay. So we're using the PD compensator. Proportional plus derivative. Proportional plus derivative. Okay, so what is it we're trying to improve on this system? Steady state error or the transient time? Transient time. Because I'm trying to reduce the settling time. Settling time is part of the transient response. Okay, so how do we design the compensator? What is the first step? Oh, I didn't give you the system.
Plot the axis.
First, write the system. Okay, so how do we solve this problem? We're going to design a derivative compensator that yields 16% overshoot with reduction in settling time by a factor of 3. The first step, since we are designing using root locus, is to plot the root locus. So how does the root locus look like? We have a pole at 0, we have a pole at 6. Which part of the real axis on the root locus. This part, this is gonna go this way, this is gonna go this way. Okay. What is the next step? So this is how the root locus looks like. We're gonna find where we are operating on this root locus. What is it that we're given that will help us determine where we are currently operating? The overshoot. So therefore, I'm gonna see if I'm operating at 16% overshoot, what is this gonna give me? What is it? It's going to give me the angle that theta cosine inverse of 16% overshoot corresponds to zeta, that is equal to 0.504. And therefore, from zeta, I can know the angle I'm making with the real axis, which is going to equal to cosine inverse 0.504, which is equal to 59.7 degrees. Does that make sense? Everybody, remember this? Okay, so we're going to come here. We're going to plot a line What is this angle equal to? 59.7 degrees. And then what do we have to do? We have to find the intersection. How do we find the intersection? Any ideas? Long time ago? How many weeks ago? Anybody remember seeing something like this?
Yeah, you need omega n. You do the triangle.
What is it? Oh, we need to find K. We need to find K, and we need to find...
Steady state.
No, not the steady state error. We need to find K, and we need to find the operating point that we are operating at. How did we do it? I think we've done it long time ago. Maybe last week. Yeah, I think last week.
You have like zeta omega n on the x-axis.
Mm-hmm.
And then omega n times the square root of 1 minus zeta.
Does this look familiar?
Yeah, that's what I'm looking
No, it's been a while. Oh, because this was not on the exam, so nobody's studying this.
It was tangent.
I get it now. Okay, so this is how we find the location of the intersection. Of course, if you have MATLAB, we can just hover over the root locus and find the location that gives me that value of zeta. If I don't have MATLAB, I need to solve for K and for the real part and for the imaginary part. Together, so I'm going to need 3 equations. One equation comes from the tangent of the real and imaginary. Then I'm going to say this point that we have here belongs to the root locus, so it's going to satisfy the characteristic equation. that characteristic equation is going to give me two equations, one for the real part, one for the imaginary part. And therefore, I'm going to have two unknowns, which is the real part and k. I can solve for them. Okay. I mean, the math is a little bit tedious, but we should know how to do it if we have to. Okay, so nevertheless, we're going to find this intersection. And the intersection point is at negative 1.205 plus or minus j 2.06. And this corresponds to k, that is equal to 43.3. So this point here, the location is negative 1.2, and the y value is 2.06. Is that clear? Yes? Okay, so what do we do next? So here is where we are operating. Find the settling time? Yeah?
Yes.
Excellent. We're going to find what the current settling time, because it's asking us to improve the settling time from where we are operating. So let's see what the settling time is where we are currently operating. So the current settling time equal to 4 divided by zeta omega n, if you remember. What is zeta omega n equal to? What is it?
5.504 times.
Which one?
Yeah, negative.
1, yes, 1.205. And therefore, the current settling time is 3.32 seconds. Make sense? Remember, the real location is 4 over that real location is the settling time. Of course, when we are doing all this, what is the implicit assumption we're making? We're assuming this is a second order system or behaving like a second order system. All this applies to a second order system. Okay, so what is it we're going to do? We're going to calculate the new settling time. What is the new settling time going to equal to? We're going to improve it by threefold. So we're going to have 3.32 seconds divided by 3, which is going to equal to 1.107 seconds. Together? Okay. So therefore, what is the new settling time tells me? What zeta omega n has to be. Excellent. So from settling time, I know that the settling time is gonna equal to 4 divided by zeta omega n nu, and therefore zeta omega n nu is gonna equal to 4 divided by 1.107, which is gonna equal to 3.63. So what does this give me? The real coordinate of the operating point. So I'm going to come here. This is 3.63. I'm going to go here, and this is my new operating point. Make sense? How do I know the y value of this operating point? What is it? Along that line. Yes, so I can take the tangent of 59.7 is going to equal to y nu divided by the 3.63, which is going to give me y nu equal to 6.19. So this new operating point is a 3.63 or negative 3 plus j 6.19. Good? Okay. So what do I do now?
Aren't you off the root locus?
What is it?
Aren't you off the root locus?
Yeah.
So you need to move the root locus.
Yeah.
Change the dynamics of the system.
Excellent. So I was operating at this point. Now I need to be operating at this point, but this point is no longer on the root locus. So what do I have to do? I have to change the shape of the root locus. So now it goes through this point. Make sense? So therefore, I'm going to come here, start a new page. If I look at how the system looks, I have a pole at the origin, I have a pole at -4, I have a pole at -6, and now what I want to be operating at a point that is here, that is -3.63 plus j 6.19. Make sense? How do I, and this is currently not on the root locus. How do I make this on the root locus?
You have to add a pole and a zero.
I'm going to have to add poles and zeros. What is the criteria that we're going to use to make this on the root locus?
Angles criteria.
The angle criteria. Yeah, the angle criteria. I want the summation of the angles from the zeros minus the summation of the angles from the poles to be an odd multiple of 180 degrees. Okay. So therefore here, I'm going to say using angle criteria. What I'm going to do first, I'm going to see how off I am from 180 degrees. So therefore, I'm going to come to the poles that exist and the zeros that currently exist, but I don't have any zeros that currently exist. I'm going to calculate the angles from all these locations. And then I'm going to use the angle criteria to see how much I need to add to be on the root locus. Okay. So if I look at this angle, what is this angle equal to? What is it? 120? Close enough. It's going to equal to 180 minus this angle. What is this angle? Tangent inverse of the 6.19 divided by the 3.63. See it? So I'm going to plot another line here that is the actual location of this pole. Okay. So this is going to be 180 minus tangent inverse 6.19 6.19 divided by 3.61. And this is going to give me 120.3 degrees. So the angle it makes with the first pole is 120 degrees. What is the angle it makes with this pole here at the 4? What is this angle going to equal to? You know which one? This one. Y over X. What is Y? 6.19. What is this distance?
4 minus, like, or 4 minus 3.63.
Yeah. 6.19 divided by 4 minus 3.613. Together? Now, I mean, don't be very confused on these locations are negative, but we're looking at distances. Does that make sense? So, like, you don't want to, oh, this distance 6 over negative, this is not, this is a positive distance. Okay, so this is going to equal to 86.3 degrees. And then finally, I'm going to calculate this angle. What is this angle going to equal to?
6.19 over 6 minus 3.63.
Very good. Okay. So, therefore,
What is that angle?
Should that be the,
which one?
Still 86.3, or is it?
yeah, you read the same thing as the last one.
Oh. Good catch. No, it's not 86.3. What's the odds of it being? Now people are not going to trust it. It's going to say, oh, he wrote 86, now he's 68. Fine. He's insisting. Okay. Okay, so using the angle criteria, we want the summation of angles from zeros minus the summation of angles from poles to equal to any odd multiple of 180 degrees. Okay, so let's calculate what the current angle is going to equal to. So I'm going to call the angle that we need to add as phi compensator, that we do not know, that I need to add. Then I'm going to add the angles from the poles. Is going to be negative 120.3 minus 86.3 minus 68. And I want this to be plus or minus 180 degrees. Make sense? I want these to add up to either positive or minus 180 degrees. And therefore, I want my compensator, or the smallest compensator angle, has to equal to 95.6 degrees. Does that make sense, everybody? If I add these together, this is going to be around 270. I'm going to move it to the other side, and therefore I'm going to have 270 minus 180, which is going to give me 95 degrees. Okay. How do I add a compensator? Or, of course, this is the compensator. This positive angle is going to come from a 0. Make sense? Otherwise, if it was a pole, it's going to be negative. I need to add a positive angle. Okay. So therefore, I am operating at this point here at negative 3.63 and 6.19, and I want a 0 to give me 95.6 degrees. Where is that 0 gonna be?
To the right of negative 3.6.
Excellent. It's gonna have to be to the right. Why? Because if it was here, how much is gonna give me? 90 degrees. If I move it here, what is the angle gonna be?
Less than
Less than 90. If I want more than 90, it has to be to the right. So therefore, I'm going to write an angle that is 95.6, which is slightly greater than 90 degrees. I'm going to define this distance here as delta. How do I find the location of this 0? What is it? I'm going to take this angle here, which is 180 minus 95.6. The tangent of it is going to equal this distance, which I know, divided by delta. And therefore, this is going to give me delta that is equal to 0.6. Therefore, the location of the 0 is going to be at negative 3.613 plus 0.6, which is going to equal to negative 3.01. So this is going to be at negative 3.01. So therefore, my controller is going to equal to K multiplied by S plus 3.01. Where are we going to place the pole for this controller? There's no pole for this controller. Why there's no pole for this controller? By design, because we are using a PD compensator. It only has a 0. There is no pole. Okay. Okay, let's run some MATLAB quick and Okay. So this is, of course, not very easy to see looking at these, and well, maybe it is not as hard as maybe it appears. I thought at the beginning I did not set the same axis size, but they are the same axis size. So this is without a compensator. We were operating at this point here. Now with the compensator, we are operating at this point here. We added a 0 such that now the compensator, I'm operating at this point here. Make sense? So what I'm going to do, you guys going to study this at certain point, aren't you? Promise? Okay, at certain point, you're going to come back and look at this. And hopefully, when you do that, you can run it. You can just copy paste it. Sounds good? Any questions? Straightforward. PD compensator, trying to improve a transient response. Now we know when we want to improve the speed, what do we have to have the pole? What does have to happen to the operating point? It has to move away from the origin. Make sense? So when I was operating here, if I want to get faster, I have to move farther from the origin. So at 3 times improvement, it means I have to go 3 times the distance from the origin. Okay. So in this case, it was the requirements was giving in terms of settling time. It could have been anything. I will find where I'm operating, or if I know where I'm the new operating point, I can just mark the new operating point, and I want the angle criteria such that I'll be operating at that point. And I'll find the contribution of the 0 that will give me that location. Make sense? Okay. Finally, or not finally, the next compensator that we're going to look at is the lead compensator. And the lead compensator uses a passive circuit. R2, R1, C, V output over V input is going to equal to S plus ZC divided by S plus VC. And you can derive these in terms of the R1 and R2. Can anybody tell me how is this circuit a high-pass filter? Or is this circuit a high-pass filter?
Low frequencies will be no. Because the capacitor
Yes, what does the capacitor act at low frequency?
is it a short circuit or is it a open circuit? I'm not sure.
Did you ever see a capacitor working with a battery?
I'm sure one of the lines.
It's an open circuit.
It's an open circuit. It's an open circuit. If it's an open circuit, then what is the output over the input going to be? R2 over R1 plus R2. So it's going to be a portion of the input voltage. If, on the other hand, the frequency is very high, frequency goes to infinity, what is the capacitor going to be? Short circuit. If it is short circuit, what is the output going to be? What is it? It's going to equal the input. If it is short circuit, if this is a short circuit,
Yeah.
what is the output going to be? The input. Okay, we'll write it and erase it. If the capacitor is a short circuit, it means it's a short circuit. So this is the input, this is the output. Make sense? There is a resistor, but then this is short-circuiting it with the capacitor. What is the output? The same as the input. Make sense? So what's happening? At very high frequency, the output is equal to the input. At very low frequency, only a portion of the input is at the output. So it is a high frequency. It is a high-pass filter. Okay. Okay, so what we're going to be doing with the lead compensator, we have a pole and a zero that we're going to be adding. And unlike the lag compensator, we're going to have the zero. This is theta p, this is theta 0. We're going to have a 0 that is closer to the origin than the pole. So therefore, the contribution, the angle contribution of the lead compensator is going to equal to theta z minus theta p, and this is going to be greater than 0. Apparently, this theta z is greater than theta p. So the contribution of the 0 minus the contribution of the pole is going to be positive. So therefore, this compensator is adding positive angle. Okay. So therefore, to design the lead compensator, we're going to select dominant second order pairs, and we're going to find the required angle to meet angle criteria. Similar to what we've done in the lead compensator, but now we have more flexibility. We have a pole and a 0 to meet that angle criteria. So here, we're gonna, as we're gonna see in the next class, we're gonna have multiple solutions. So if I want to add, I can have multiple locations that will contribute. So all of this, theta z minus theta p equal to theta critical. So this is what I need to be operating at that point. I need a pole and 0 such that the difference between them is theta critical. Is that clear? Semi-clear. We'll do an example next class. Now, just one thing I forgot to mention. If I look at the lag compensator, if I look at the phase angle of the frequency response, we see it is negative. That's why we call this lag compensator. When it is positive, we call it lead compensator. Okay, thank you, everybody. We'll see you on Wednesday.